And the first speaker is Crafoord Laureate Conny Aerts from Leuven, and she will tell us about Beyond Sun-like Stars. Thank you.
I hope I get my clicker. Okay, thank you, everyone. Let me first add my gratitude to the Crafoord Foundation and, of course, the Swedish Academy and everybody who's making these days happen. It's a memorable week already, and we're only at the first day, so thanks for that. I advise you to buckle up a little bit, because we're going to go faster. And that's because the stars I treat beyond sun-like stars are moving faster in terms of their rotation, okay? So let me also go back a little bit and mainly address maybe some of the non-astrophysicists in the audience and, you know, ask us the question, why do we care about stars in the first place? And I also want to make sure I address the youngsters far in the back in the audience there, because you're my most important audience, I would say. You're the future. Stars are beautiful for most people, probably inspirational, certainly for artists and, well, actually all human beings, I would say. They are vital in many ways for astrophysicists, but also for the average properties of us here on this planet Earth, right? And therefore, I like to start my lecture with chemistry. I'm not a chemist, but I do know that the chemical table that most of you may have seen in their education is of critical importance for everything that is happening here on this planet. And why do I show this? Because we are here thanks to the stars. Stars created all the chemical elements, aside from hydrogen and helium, that were given to us in the Big Bang, and a little bit of lithium. All the other elements here are created in stars. And so what you see in this table is the evolution of how much of each material is what we think present in the universe from the Big Bang until the present day. And so you can pick your favorite elements, and they are indicated where they came to be thanks to which stars. So anything that we have here on Earth, I always say, like, touch your hair if you have hair, touch your jewelry, touch your furniture, it's all made by the stars. So let's be grateful. Now, this prediction completely depends on the models of stars that we have. And as you have heard from Douglas and Jörn, we don't know everything about the stars, and there are quite some caveats that we still don't know. And so, Beyond Sun-like Stars is the title I chose to move up in mass, mainly, and along with it in rotation speed, and see how much we know from astroseismology about these stars. So, in this picture, this sort of captures the life and the evolution of stars in one graph. And everything we heard this morning was on the left side. You know how sun-like stars are being scrutinized thanks to their solar oscillations, solar-like oscillations, even when they evolve towards red giants and then enter in the stellar graveyard as a white dwarf. Yeah? These stars live a fairly quiet life. Very decent, I would say. Now, if stars are born with about 8 times more or even more mass than the sun, they don't go to the left of this diagram. No, they evolve to the right. And they do so at a tremendously high speed compared to sun-like stars to end up in the graveyard of neutron stars and black holes after they had a Big Bang supernova, right? Now, this part of the diagram hasn't been touched upon yet, and so that's what I will do. Well, these stars live billions of years, as you've heard. These ones only live millions of years, so that's why I said buckle up. It's super fast in terms of astronomical timescales. And as Jörn explained, the timescale Why is that actually? It goes like the mass over the luminosity. The mass is higher, say 10 times. But what's more important, the luminosity is really rising dramatically if the mass goes up. So if you divide the mass by the luminosity, then you have a way, way smaller number. So millions instead of billions of years, right? Now, these stars are also a bit different in their construction. And here I am showing a slide, a schematic slide of the computer models that we have of stars. So basically we write beautiful mathematical equations, we turn them into operational computer codes to make the computations, and we evolve them over billions of years for solar-like stars, millions of years for massive stars. In practice, stellar masses can go very roughly from about 1/10 of the sun up to 100 times the solar mass, right? And so the consequence of that is that we have thousands and thousands of generations of massive stars already exploded and in the graveyard compared to sun-like stars. But even so, at lower mass, these stars that have been born after the Big Bang in this universe, well, they're still in their childhood because they had no time to evolve yet. Now, for all of these masses, we need stellar models to predict that chemical table and its evolution box by box of all the chemical elements. So we need these models to compute ages. That has been made clear very clearly by Jörn. The energy budget of all the objects in the universe, and we want to have life cycles, coming back to all the materials that we have in this galaxy, in our neighborhood, including our planet. Well, that chemistry has been built up by all the life cycles of all these stars. And so we have to scrutinize the models to a higher precision. And that's where astroseismology comes in. Again, here is a very schematic diagram that builds on what Douglas and Jörn explained. Sun-like stars, and even lower, well, they have this convective outer layer, remember? And that's what creates what is often called noise. I don't like the word stellar noise. I prefer the word stellar music because it just sounds so much better to me, okay? So these stars you are all experts in now. I mainly focus on these stars, where actually the turbulent convection sits inside the core. And it's a radiative outer layer compared to the opposite in the sun and in solar-type stars. Yeah? So you have, I think, understood that our knowledge is limited in the area of these convective layers, and particularly the transition layer. That's hard. Now, this is important for the sun and sun-like stars, but I would dare to say it's much more important for these types of stars. Why? Because here the transition layer immediately determines how much mass enters the convective core of these stars and takes part in the nuclear fusion. And it's the nuclear fusion that determines the life path and the age of a star, right? And so our unknowns are exactly as in sun-like stars in the transition layer between the convective turbulent motions and the radiative layers, but this time it sits inside the star, in the deep core of the star. And it's hard to get there, as Douglas and Jörn explained so beautifully. It's the same for me. But the position and the physics of this transition layer is really crucial. And so we are trying to get information via the oscillations of the massive stars. Now, they live much faster. They also rotate much faster. Why is that? Because here, the sun and sun-like stars are really slowed down by something we call magnetic braking. So the outer convective layer is really implying that there is a loss of angular momentum for these type of stars, and that is how the sun gets to its rotation period of about 26 days with a high precision measured, as you've heard. But these stars, where here the convection sits inside, and in the outer layers there is no magnetic braking, because it's a radiative outer envelope. And so these stars are born with fast rotation like all stars, but they don't get rid of their fast rotation because they keep their angular momentum, unlike in solar-type stars. So they rotate way faster. And if you rotate much faster, then the effects of the Coriolis force and the centrifugal force become very important. Right? And so we have to deal with that as seismologists of like anything beyond sun-like stars, let's say. Now, testing stellar models, how was this done prior to astroseismology? Well, we are very good technologically in putting a lot of euros and other currencies in building instrumentation both from the ground and from space to observe stars, as Douglas said it so beautifully, from the outside, right? So classical observations at high precision also are available, and that is being used to test what I call the house of astrophysics. Whether you do exoplanets, very modern, gravitational waves, galaxy studies, astrochemistry, black hole, supernova, you name it, there is one thing that you usually need to understand all these sources, namely the connection between observations and models. And this is reality. Reality is that we use stellar models assuming that stars are spheres. And you have heard how wonderfully good this is for the sun. It's fantastic, right? It's not perfect, but it's great. And so when I say 1 + 1D, I mean we describe stars as spheres, one spatial dimension, and time. We evolve them over time. Now, black holes, supernovae, they result from massive stars. Massive stars are not slowed down effectively. And if you have fast rotation, then you have the centrifugal force. And this implies, given that stars are spherical, hot gaseous bodies, these stars are not spheres. They're spheroids. They're flattened by rotation. Right? And so we need to take care of this. And here's an image of Altair, which is such a star. This is not a sphere. And so our models are really in need of improvement. Right? And so the challenge that we, astroseismologists of massive stars, face is that the models are not really good to describe rotation, convection, and magnetism. These are three-dimensional phenomena that we try to squeeze into one-dimensional prescriptions. And so that's not optimal. It's pretty good for gravity and nuclear reactions and thermodynamics, but it's not good for macroscopic motions, as I call it. And this can give systematic uncertainties for ages up to a factor 1,000. That's, I mean, the sun and helioseismology has sort of like downgraded a little bit from 0.5% to 2%. That's fantastic, 2%, right? I'm dealing with stars where we have to fix this. Yeah? And these models are being used by many of the astrophysicists. Can we do that? Yes, we can. You know by now how we do that, by using the waves, seismic waves of stars, that are actually probing locally, as Douglas has explained it so beautifully this morning. They probe locally the internal physics. And what I like are these, I think it was indicated in purple in the slides of Douglas, that go straight through the center of the star, because that's where all the action is in terms of stellar light. Yeah. And you also know by now we can measure this with 1 in a million as a precision, right? It's not different from sun-like stars. And here is one beautiful example, a star measured by the Kepler space mission, where you see its seismic activity indicated. It's a 15-day time scale, but in reality we have 1,500 days. As Jörn explained, we have 4 years uninterrupted data. This star has big oscillations, parts per 1,000. That's way bigger than the sun and solar-like stars, right? So it's a bit easier in terms of detection, but it's a bit slower. Why? You know also by now why. The bigger the star, the slower the oscillations are, provided we're talking about acoustic waves, right? Now, how do we improve these stellar models, or how do we test them? Well, on the, what is it? I'm bad in this. Right-hand side, you have observations, the space photometry, the beautiful data, and note, by the way, that before we get such a beautiful light curve, we have a whole lot of engineering and instrumentation and software development on data analysis. I like to stress that because I think the three of us are more on the modeling side, but there's a whole lot of people working for us to get such beautiful light curves. And it's, as Jörn said, it's important to recognize the team efforts of the consortium that we are happy to work in. And then you have all these beautiful frequencies. You understand already how this works for sun-like stars. And each of these peaks here is one of these modes, spherical harmonic functions, as it was explained to you. The hard time we have in massive star astroseismology is to label each of these peaks with a spherical harmonic. Why? Well, when stars are flattened, we have to abandon the beautiful spherical harmonics. We have more complex mathematical functions. And we can handle that, but there was nothing telling us how to handle it until 2015, actually. And so if you have to deal with functions that are in spheroids, then it's not the same than functions in spheres. That's why we love spheres. But yeah, that's a challenge here, moving from here to here, identified frequencies. But the bigger challenge is on the left. The theory that we have, simple stellar models, they're not that simple, but when I say simple, I mean they're spherical models, one spatial dimension, okay? And we predict their oscillations, we predict how they should behave in such diagrams. So we predict theoretical frequencies, we compare them, but remember, this is at a very high precision. Yeah? And so this usually doesn't work when we compare. When I mean doesn't work, that means that our theory is not able to explain the observations up to the precision measurement of the frequencies, okay? So let's look at some oscillations. Here are some animations, because really what I have to care about more than Douglas and Jörn is that the rotation goes at almost the same speed, or the same period, I should say, than the oscillations, right? And so in that case, you cannot ignore, as you can do it for the sun and sun-like stars in first instance, that the gas is rotating. The rotation really gives a frequency shift, right? A frequency shift that is almost as large as the value of the frequency itself. So this is very different from acoustic waves in sun-like stars, where the acoustic waves, well, they have periodicities of 5 minutes, as you've heard, for the sun, and the rotation of the sun is 26 days. Well, 5 minutes divided by 26 days, that's a very, very small number. That's tiny. And so that's why Douglas and Jörn can ignore the Coriolis force in the first place to do their global seismology. But my stars, well, nobody owns stars, but so to speak, yeah? The massive stars, well, they rotate in a period of about like a couple of days, let's say, say 10 times faster than the sun, roughly. But their waves are so much slower. Yeah? They're facing gravity waves, as Jörn introduced them in the end of his talk. And so the periodicities of these waves are also about 2 days, which means that you cannot pretend that while you study the wave motion, that your star is not rotating. You can't do that. That's not good enough, okay? And so that's why I have to care about these things for stars that have turbulent convection in their core, okay? All right, so how do we do that? Well, here I'm adding 2 forces in the description, in the physical and mathematical description of the oscillations. It's not needed for the sun, as we have seen, but it's needed for stars that are later going to explode as supernova. We have to care about the Coriolis force, and if they are magnetic, about the Lorentz force. And this makes them deviate from spherical symmetry, okay? is this difficult? Well, it costs more effort. We know how the Coriolis force looks like. We know how the Lorentz force looks like, well, if it's a simple magnetic field. So we can do that. Why wasn't this done before? Because it's not necessary for sun-like stars. So we don't want to complicate things if it's not necessary. And that's why helioseismology led to a great heritage for sun-like stars, for red giants. But for massive stars, we don't have a sun to calibrate our methodology, right? Because the sun is such a slow rotator. So it costed a bit of effort. And so I try to simplify things by showing it to you this way. We have a frequency axis, and here are Jörn and Douglas, completely on the right. High frequency acoustic waves in slow rotators. Yeah? Now we move here, and 2 omega is twice the rotation frequency. Now we have slow waves in fast rotators. And so we are on this side of the diagram. And there you get different types of waves, internal gravity waves, again, introduced by Jörn. But let's imagine that the Coriolis force is the dominant force over buoyancy. Then you have what we call inertial waves. We know them. They happen also in this planet, right? And so the interaction sort of between inertial waves and internal gravity waves then creates what we call gravito-inertial waves. These are waves restored by both buoyancy and the Coriolis force at the same time, because these forces come together, let's say, okay? And so in that sense, we have to develop a new methodology to understand the beautiful data. Here I have this famous gallery created by one of my students, Peter Papic, and you see the gray observations from the Kepler satellite for 7 stars. Overplotted in red are the frequencies of oscillations of these stars, and you see a pattern. Remember, Jörn had a pattern like the red giants, the lower one going all the way up. That was a raise in the size of the star, so the frequencies went down. But here I'm dealing with a going down from a slow rotator in the upper panel all the way down. This is the rotation shift of the frequencies that we see. And this is big. It's a huge shift. That's the Coriolis force in action. So by just looking at this, I can derive the rotation frequency of the star. Where inside the star? Well, in the area where the waves are most propagative. And so this is critical, okay? And so now it's simple. If we look at the frequencies and see how they evolve, we can really label the rotation frequency of the star deep inside the star, near the core, where these waves have their strongest probing power. So it allows us to derive the amount of helium in the core, and remember, that gives us an age of the star. And it allows us to deduce the Coriolis frequency, which then tells us how fast the rotation is happening. Okay. Now, here is an assembly of our community after hard work by many people that shows the inner rotation frequency of the star, that's very close to its convective core, as a function of the evolution of the star. And each and every symbol in this graph is a star, and each of every symbol was a lot of work by astrophysicists together with data analysis people. And there are about 1,800 symbols in this graph in my assembly. Now, if you look at the values here, this is about 2 microhertz, right? And so all the stars that Jörn treated this morning are below this line, right? All the stars here really have waves that are so slow that you cannot ignore the Coriolis force. And so before 2016, and I still find that amazing by the day, there wasn't a single symbol here. It was empty. It was the most boring plot you could imagine. An empty window on the rotation of stars in the universe. And so now we're building up gradually, and I've even plotted the one. I love hot blue stars. Yeah, and so there's a star here 12 solar masses, as I was saying in the beginning. As of 8 solar masses, you are following a star that is about to explode as a supernova. In only a few million years, this star will end up as a supernova, providing all the chemical elements in this diagram that I showed off with in the beginning by exploding and giving its material back to the environment where it sits in our galaxy, okay? So we have a theory, a much better theory now, on internal rotation. And you know what? It wasn't only red giants where we had trouble in explaining the rotation, even at the slow level. We were facing up to a factor 100 discrepancy. This is very critical for these massive stars and their convective cores. It's not local conservation of angular momentum, as we thought it was until about a decade ago. No, there is something that makes the convective core, when it rotates fast, couple efficiently to the envelope and evacuates angular momentum. And so we have learned that this is a factor 100, 10 to 100, depending on the star, more efficient than what we thought prior to astroseismology. So this is a big service to astrophysics, I would say, in having derived that conclusion. The models are now much better. They can handle this. I'm not saying we understand the models, and that's where we have to work on, right? But we know that there are waves that can transport angular momentum way faster, and there might be magnetism that is also helping. These are the two major conjectures that have been entered into these models to get a better improvement. There would have been absolutely no other way to do that than via seismology. So we are kind of proud. Our house is a bit more stable now, right? But still, we're still treating stars as if they are spheres in our pulsation descriptions. And so actually, I'm very happy and also proud that we're now going to more complex functions. And we are trying to develop stellar evolution for spheroids instead of spheres. Now, for that, you need to describe three-dimensional bodies in three spatial dimensions and in a time dimension across millions to billions of years. And so this sounds easy, but it's not. It's just from 1 to 3 dimensions. It's not. We lose all the beautiful mathematics of the spherical harmonics. We have to go to more complex functions. We call them whole functions. But I have some more time to sort it out, thanks to an ERC synergy grant with my 3 companions here, Aaron Dotter in the US, Michel Riotor in France, Stéphane Matisse in France. So that's a beautiful aspect. Now, it's not only about improving the theory. If you do spheroidal astroseismology, you also have to care about how you look upon the star's angle of rotation. You know, a sphere doesn't matter how you look upon it. It always looks the same. But if it's flattened and it's tilted towards you, then you have to start unraveling that. And we have yet to sort out how to deal with that. We can do that for some stars where we have an actual image, but this can only be done for very bright stars. So we're going to have to estimate the inclination angle, as we call it, from the data. Let me move on to another. I have many onwards. Here is one. Well, this is from my colleague, Uksana. What is this for a graph? Probability as a function of mass. And so, again, you know, the whole mass range. And this red curve shows the probability that a star has a companion when it's born. And look at where my stars are, so to speak. Yeah? Above 10 solar masses. Well, you're almost sure they're all in a binary, whether we like it or not. If you have a binary that is in close... Now, this equipment from Douglas is... that is, the 2 stars are going around their center of gravity, right? Well, that's not very symmetrical, and that's not possible to describe with stellar models. So we're going to have to deal with another thing, that's the tidal force that I have carefully avoided talking about. And tidal waves have been observed in a big chunk of the Kepler stars. Now, another onward, as Jörn has shown, Plato. I'm very proud of Plato. And here you see me in the clean room at ESTEC with one of the lead engineers. That's to show you it's real. It's not only a design graph. It's real. We're building it. These are 26 telescopes on one platform, and it should get launched in December 2026. It will observe a field in the southern sky indicated here for many, many years, initially for 2, but we will try to get that longer, because we know the longer we measure, the better the frequency precision. And so this is going to revolutionize stars of all masses and all evolutionary stages in terms of seismology and planet hunting at the same time. So we are heading for a bright future, I would say. We've had initially the Coral space mission, where I'm still proud of. As a Belgian, we were a big part in the Coral mission. Then came Kepler for 4 years. These are the most beautiful data that we have so far. Now the TESS mission is operational right now, literally. You can take it literally, doing another type of monitoring of the sky. It monitors the full sky, while Kepler had just one field where it stared at. And so Plato is actually combining the best of both Kepler and TESS, in the sense that it will also stare at one field, but it's way, way bigger than what TESS did. Way, way bigger. So we catch many more stars, and we do it long-term and uninterruptedly. Well, the TESS mission now is going across the sky sector by sector, and only delivers typically 1 month of data. And for a person like me studying slow waves in fast rotators, well, 1 month, that is just peanuts. And I can't do my seismology from 1 month of data. I can do something, but not much. So we're really looking forward to this machine here that is being constructed. And so we have lots of engineering teams doing this type of construction and calibrating the whole machinery to become operational. So this, I hope to see the data before I retire. And well, should work. Let me end, because my time is up, by repeating what Jörn said. This is above all a great honor for the 3 of us, but we really work in teams, not as big as particle physicists, but still. And so if you ask me, and I sometimes get that question, what are you most proud of? Then my answer, well, is not that we've mapped the internal rotation of stars, even though I think I have some contribution in it. It's also not that we can do age dating of stars. That's all very important for astrophysics, and I'm very proud of these achievements. But what I'm most proud of, actually, is in my last slide. My last slides are my scientific children. So you see here a picture of all my PhD students, graduated and ongoing. There are 43 faces in this slide, of big diversity, very different people from all over the world, different gender balance, different identities, different religions, and they keep me alive and kicking. So I would like to bring a tribute to my students, because it's thanks to these youngsters that us 3 oldies are standing here, actually. And I insist on giving that as the takeaway message, and to encourage youngsters to follow their dreams, whatever that may be. Thanks a lot.